All right. Today we're going to talk about rational functions, horizontal asymptotes, and graphs. And we're also going to do slant asymptotes and other asymptotes as well. Horizontal asymptotes determine the end behavior of a graph as our x values get large. So let f of x equal a to the n over b to the d power be a rational function whose numerator has a degree of n and denominator has a degree of d. The graph of the rational function has at most one horizontal asymptote as follows. So if the degree of the numerator is less than the degree of the denominator, so this is case one. So the numerator degree is less than the denominator degree. Then we say we have a horizontal asymptote at y equals 0. If the numerator degree equals the denominator degree, then there's a horizontal asymptote at y equals a over b, the ratio of the leading coefficients. And if the numerator degree is greater than the denominator degree, then there is no horizontal asymptote. Instead, we have a slant or other asymptote. To find the slant/oblique asymptote, we divide the two polynomials, and the quotient polynomial is the asymptote that describes the end behavior of the graph. So horizontal asymptotes y equals b. The graph behavior will approach the horizontal line as x approaches plus or minus infinity. That is, if we have the limit as x approaches infinity and you get some value, that means you have a horizontal asymptote there. Same thing for negative infinity. So if we look at this graph, we want to look at it says, what's the end behavior of the graph to the left? So it looks like we have a horizontal asymptote right here at y equals 2. So we're going to use our limit notation to write this. So we would say, so the limit would be the limit as x approaches negative infinity for the function f of x. What are your y values doing? They're going towards this horizontal asymptote 2. And the limit as x approaches positive infinity for the function is also approaching 2. So that would be how we would write our limit and behavior for this. So the next equation say, find the horizontal asymptotes and write the end behavior of the function. So we're going to have to look at the degree of the numerator versus the degree of the denominator. So looking at this first one, again, you need to make sure that it's in standard form when you're doing this. So you can see that these equations in numerator and denominator are both in standard form. And so then we can easily see the degree of the numerator is a degree of 2 over a degree of 3. So this is where the numerator is less than the denominator. So remember that was case number 1. And so then that means the horizontal asymptote is at y equals 0. So the end behavior would be the limit as x approaches either plus or minus infinity, we can write it together, for the function f of x is approaching 0. And we did this last year, but instead of writing the limit notation, we used as x approaches infinity, y approaches 0, and as x approaches negative infinity, y approaches 0. But this is just a different way of writing it. So looking at the next one, we're in standard form for both the numerator and denominator. My lead terms are 3x squared over 2x squared. So this is a degree of 2 over degree of 2. So that means the numerator degree equals denominator degree. This is case number 2. So that means we have a horizontal asymptote at the ratio of the leading coefficients. So that would be 3 over 2. And so then the limit as x approaches plus or minus infinity for the function is equal to 3/2. Looking at C, same thing. So for this one, we're looking at the degree of the numerator versus denominator. It's in standard form. So we have a degree of 4 over a degree of 6. So this is case 1. Numerator of degrees less than denominator degrees, so the horizontal asymptote's at y equals 0. Let's circle that there. And then that means the limits as x approaches either plus or minus infinity, positive or negative infinity, for the function f of x is approaching 0. And I guess I should use g of x for this one, sorry. Going back here, because it's g of x here, not f of x, and this one's p of x. I wasn't really paying attention to the actual function name. Sorry about that. So make sure to fix those two. Looking at question D, notice this is not all one function, so it's difficult to spell the standard form, but I know that this plus 4 means my graph's moving up 4, and if I look at just this right here, that's a degree 0 over degree 2, which means the horizontal asymptote would be 0, but we're moving our graph up 4. So I actually know there's a horizontal asymptote at 4. But if we can't see that, then we should make this into one fraction by getting a common denominator. So that means I would have to multiply this by x squared plus 1 over x squared plus 1 to get a common denominator. So when I do that, I get x over x squared plus 1 plus, and then we're going to distribute here, 4x squared plus 4, I'm going to fix that, over x squared plus 1. Once you have a common denominator, you can combine your numerator over your common denominator. So 4x squared plus x plus 4 over x squared plus 1. Now this is one fraction, so you can see the lead term here is 4x squared and x squared. So this one, your numerator degree equals the denominator degree. So that means the asymptote would be the leading coefficient. So the leading coefficient in the denominator is 1 and the numerator is 4. So that means we have a horizontal asymptote at y equals 4. And so for our end behavior, the limit as x approaches plus or minus infinity for g of x, because that's our function, is equal to 4. And again, you could have seen that from the original equation because you can see right here, this approaches 0, but you're adding the 4, which means if you think about your transformation that goes up 4, just two different ways of looking at the problem. Looking at this one here, again, we're in standard form, the numerator and denominator. So this one has a degree of 3 over degree of 1. So this one, the numerator degree, is greater than the denominator degree. So remember, that means there is no horizontal asymptote. So if there's no horizontal asymptote, then how do I find the end behavior of the function? This is the case where we have to do either long division or synthetic division to solve. So remember, if we're dividing by a linear binomial with a leading coefficient of 1, we can use synthetic division. So in this case, we can use synthetic division. So in the box is the 0 of the denominator, so that would be 1. And then our coefficients are 1, 3, and then, so we have degree 3, 2, 1, 0. So 1, 3, 1, 1. So I was just making sure I didn't need any 0 placeholders. Bring down that first term. 1 times 1 is 1. Add these together to get 4. 4 times 1 is 4. Add these together to get 5. 5 times 1 is 5. Add these together to get 6, and that's your remainder. So if this is a degree 3, that means this starts off with degree 2. So this would be x squared plus 4x plus 5 and plus 6 over x minus 1 is how we used to write that. However, when you are writing your end behavior, and we talked about this in Math 3, you don't need to include the remainder because it's so small. So we would say, and notice that the degree difference from the numerator and denominator is a degree difference of 2, so it makes sense we're getting a quadratic asymptote. So this is actually called a parabolic asymptote. And so we have a parabolic asymptote, and again, we don't include the remainder when we're writing it. So at y equals x squared plus 4x plus 5. And I'm going to make this a little bit smaller so I have more room to write the end behavior then. So then for the end behavior, we have to think about what we learned in our polynomial unit. So this is a degree of 2, which is even, and the leading coefficient is positive. So even positive means both ends are going to go up for the end behavior. So that means that the limit as x approaches either plus or minus infinity for, what is this, f of x is the function, is going towards positive infinity. So this would be the end behavior. Looking at the next one, we have g of x. And so this is in standard form of numerator and denominator. So this is a degree 2 over degree 1, which means the numerator is bigger than denominator. So then there's no horizontal asymptote. And then we want to figure out how to get our, in this case, the degree difference is 1. So it's going to be a slant asymptote or oblique. So when we divide, we can use synthetic division because this is a linear binomial with a leading coefficient of 1. So -5 goes in the box. And we have 1. And notice this is quadratic and this is constant. So we're missing a 0 placeholder for the linear terms. So bring down that 1. 1 times -5 is -5. Add these together to get -5. -5 times -5 is 25. And then add these together to get 4 for the remainder. So then since this is degree 2, this starts off with degree 1. So this would be x minus 5 plus 4 over x plus 5. But again, we don't need to include the remainder. So we have a slant asymptote at, and usually I abbreviate SA for slant asymptote, y equals x minus 5. And I should circle this one over here. So I'm going to go ahead and make this a little bit smaller so I have room to write the end behavior. Whoops. All right, so move that over. And let's do the end behavior. So to find the end behavior, whoopsies, we need to look at our slant asymptote. So this is a degree of 1, and that's odd. The leading coefficient is 1, which is positive. So odd positive means the left end goes down and the right end goes up. So we have to write this separately. The limit as x approaches positive, well, let's do negative infinity first because that's the left side. Negative infinity for g of x goes towards negative infinity. And the limit as x approaches positive infinity for g of x goes towards positive infinity. So that's just to remind you guys of last year and how to find the horizontal asymptotes of your graph. So this one says, find the horizontal asymptote and write the end behavior of the function. So looking at this function here, notice that this is not a polynomial divided by a polynomial. We have a polynomial divided by an absolute value. And so for a rational function, remember, we only have one asymptote. Something like this, though, and I'm doing this problem just to show you, you can have more than one horizontal asymptote if it's not a rational function. So if we look at this, we can still kind of use the same idea. This is still considered a degree 1 over degree 1, even though we have the absolute value bars. So the numerator degree equals the denominator degree. So with absolute value, the difference is, remember when you're solving absolute value equations, like if I'm solving the absolute value of x equals 6, well then we know x can be equal to 6 or x can be equal to -6, because if you plug in -6, you're taking the absolute value and that's equal to 6. So you actually have two solutions here. So if you look at this problem, you would have y equals 5x over just the answer. And then we have y equals 5x and then the negative of the answer. So remember last year when we did math 3 and in math 2, we solved our absolute value equations and we did the positive and the negative. So that's where that comes from. So here, if you simplify this, you get y equals 5x over -10x minus 2 when you distribute that negative. So notice that this one, we have a degree 1 over degree 1, and the horizontal asymptote is y equals 5 over 10, which, excuse me, would be y equals 1/2. And here, because we have the negative of the answer, we get a horizontal asymptote at y equals 5 over -10, which equals -1/2. So we have two asymptotes, y equals 1/2 and -1/2. So then how do we tell the end behavior for this one? So the positive answer is to the right and the negative answer is going to be to the left. So this would be the limit as x approaches infinity, or let's do negative infinity first, for f of x is going towards -1/2, and the limit as x approaches infinity for f of x goes to +1/2. So let's actually look at the graph for this. Let me get my calculator up. So if I want to graph this, I go to my y equals, I'm going to do parentheses 5x divided by, and remember to get absolute value, you can go to math and you can scroll to number and then it's the first one right there. Or the other way you can get it is to, oops, hold on, just to go to your catalog and it's the first one. Second zero is the catalog and it's always the first one, which is kind of easier. Usually I do that a lot. So we have 10x plus 2. So let's go ahead and look at this graph soon, 6. So now you can even see, and I'm going to zoom in a little, well, I guess I can use the trace. So if I trace over, you notice that the left side is approaching negative a half. It's getting closer and closer. And if we go to the right side of our graph, you'll notice it'll be approaching 1/2. And even if I keep going and going and going, it's going to just be approaching that 1/2. So we can see that is our limit behavior. And like I said, this is not a rational function, but I just wanted to show you that a graph doesn't necessarily only have one horizontal asymptote. It's just for our rational functions. So next we're going to talk about analyzing the graphs of the rational functions, which is something we did last year. So we're going to be doing all these steps, and I'm just going to talk about them as I go rather than read through them. So let's look at each problem and figure out how to graph this. So when I'm doing these problems, I always like to first factor the problem if I can. So this one doesn't factor anymore. So then I'm going to look at the zeros of the denominator. So remember, these are the zeros of the denominator. So if we set this equal to 0, we get x equals 2. So we need to figure out if x equals 2 is a vertical asymptote or whole. And we talked about how to do that. So if I plug in 2 into my equation, because this doesn't simplify, I know that it's going to be a whole of my graph because I'm going to get 3 over 0, which is undefined. Or sorry, I said whole, a vertical asymptote of my graph because it's undefined. So we have a vertical asymptote at x equals 2, and that means there's no holes. In order to have a hole in your graph, you have to have a common factor between the numerator and the denominator, and it has to cancel out of the denominator, which we don't have any common factors here. So then the domain would be all real numbers except for 2. Then if we want to find the x-intercept, remember to find the x-intercept, we set the numerator equal to 0 and solve. As long as they're not zeros of denominator. Or I guess we should set the whole equation equal to 0, I should say. But when you do that, you're going to be multiplying both sides by x minus 2, so that cancels out, and 0 times x minus 2 is 0. So we get 0 equals 3, but 0 doesn't equal 3, so that means there are no x-intercepts in this case. Looking at the y-intercept, we plug 0 in for x, so we're going to do g of 0, which gives us 3 over 0 minus 2, which gives us negative 3/2. So we get 0, negative 3/2. And then looking at our horizontal asymptote, the numerator degree. So we have a degree of 0 over a degree of 1. So that means the numerator degree is less than the denominator degree, which means we have a horizontal asymptote at y equals 0. So let's go ahead and start to graph this on our graph. All right, so we have a horizontal asymptote at y equals 0. I should probably make that smaller. And a vertical asymptote at x equals 2. I like to always graph these first. And so remember that our graph is going to follow our asymptotes. So we just need to figure out where our graph is located. And so you have different regions. You should always have something to the left and the right of your vertical asymptote. So our vertical asymptote is at x equals 2. So to figure out what's happening, we can use our y-intercept to the left of the vertical asymptote. So we have 0, negative 3/2, which would be negative 1.5 right here. That point then tells me that I'm in this lower region below my horizontal asymptote. So I'm going to follow along my horizontal asymptote here. And then my vertical asymptote, we're going to follow on the left side going down towards negative infinity. because we were in that lower region below the asymptote. So how do we know where we are to the right of x equals 2? You can do this two different ways. Last year, we just told you guys to plug in the value and see what it was equal to and solve, which you can do. So if you wanted to do g of 3, because we don't want to use 2 because we know it's going to be undefined. So if I plug in g of 3, I get 3 over 3 minus 2, which gives me 3 over 1, which is 3. So I know I have the point 3, 1, 2, 3. So that tells me I'm going to graph my graph in this upper region right here and then follow my asymptotes. The other way we talked about doing this when it gets a little bit more complicated than a problem such as this, it's easier to look at using the big little concept. So thinking about as you get closer and closer to 2 from the right side, so 2.0001, 2.01, etc. So if I think about x equals just 2.1 and plug that in, I have 3 over 2.1 minus 2, which is a positive number, and 2.1 minus 2 is going to give me a very small positive number. So that tells me this is going to go towards positive infinity. It's just another way of thinking about the problem. And then for this, if we look at our range is going to be all real numbers except for our horizontal asymptote. So negative infinity to 0, union 0 to infinity. And so that then gives us, helps us with our end behavior. So the end behavior, the limit as x approaches either positive or negative infinity for the function g of x is going to be equal to 0, because again, in the long run, we're approaching 0 as we get larger and larger values of x in the positive and negative direction. All right, so looking at next problem, number 2. So for this problem, we'll notice right away that this is not in factored form. So I'm going to factor both the numerator and denominator so that I can find the zeros in denominator and then look for intercepts. So when I factor this, factors to -6 that add up to x would be x plus 3 times x minus 2. And in my denominator, we have 3x squared minus 5x minus 2. So when you factor this, this becomes 3x plus 1 times x minus 2. So then for this problem, I can see I have a common factor that is going to cancel out, and that then gives me x plus 3 over 3x plus 1 for my simplified. So we need to find the zeros of the denominator before we simplified it. So the zeros in my denominator would be x equals negative 1/3 for this 0, and this one right here would give me x equals 2. So we need to figure out, are these vertical asymptotes in my graph or are they holes? So remember, we can't have a hole unless we have a common factor. So the only one that has a common factor is 2. So that tells me right away, I know that we have a vertical asymptote at x equals negative 1/3. If you don't know and you plug in negative 1/3 into your simplified answer, again, you'll notice you get f of negative 1/3 would be equal to negative 1/3 plus 3 over 3 times negative 1/3 plus 1, and that equals 0. So you get a number over 0, which is undefined. We don't even need to finish the rest of that because we know it's undefined. So if I want to figure out the hole to see if this is a hole, I'm going to plug that into my simplified answer, and if it no longer makes my denominator 0, then we know it's a hole. So if I do f of 2 into my equation, I get 2 plus 3 over 3 times 2 plus 1, which gives me 5 over 6 plus 1 would be 7. So 5/7 is going to give me the hole of my graph, the y-coordinate. So that tells me this is a hole at 2, 5/7. So then the domain comes off of these two values. So we have all real numbers but negative 1/3 and 2. So negative infinity to negative 1/3 union, negative 1/3 to 2 union, and then 2 to infinity. So then my x-intercept, if I want to find that, I set the numerator equal to 0 and solve, but it can't be 0 as a denominator. So that's why I always tell students to use the simplified form, so then you don't have to worry about common factors. So we get, for the x-intercept, that's when we set y equal to 0 and solve. So we would get 0 equals x plus 3 over 3x plus 1. So if you multiply by both sides by 3x plus 1, you notice that cancels out, and this is just times 0, which is 0. So we get 0 equals x plus 3, so that means x equals to negative 3. So our x-intercept is at -3, 0. Then the next step is to look at the horizontal asymptotes. So the numerator degree is 2 over degree of 2. So the numerator degree equals the denominator degree. So it's the leading coefficient. So this is in standard form right here. We don't want to use the factored form. And we get 1/3. But you could use the simplified form as well. It has the same behavior. So this is also 1/3. So it doesn't really matter if you use the original or this one. Sometimes just in case you factored incorrectly, it's just to make sure you get this answer correct, it would be good to use the original equation. So horizontal asymptote is y equals 1/3. And then let's find our y-intercept as well. So f of 0 is equal to, and again, you can use either the original or the simplified. I'm going to use the simplified in this case. So 0 plus 3 over 3 times 0 plus 1, which gives me 3 over 1. So the y-intercept is 0, 3. All right, so let's go ahead and start to graph this. So I have my asymptote at 1/3. Hard to graph this one. And then I should use a smaller point. So then at -1/3, I have my vertical. So then for my graph, I have a hole at 2/5/7, which would be above this asymptote. So it's going to be really close right there. And then we have an x-intercept at -3, 0. And a y-intercept at 0, 1, 2, 3. So this graph is kind of nice because on either side of the vertical asymptote, we can see we already have points. So that means this is just going to follow your asymptotes above your horizontal asymptote, and this one's going to be below. So it'd have to go down towards -infinity here. So then the end behavior would be the limit as x approaches plus or minus infinity for the function f of x is going towards the asymptote, which is 1/3. Because remember, it always follows your horizontal asymptote. So the range for this one would be all real numbers except for the asymptote and where that hole is on our graph, the y value of the hole. So the range would be -infinity to 1/3, union 1/3 to 5/7, union 5/7 to infinity. All right, let's do the next one. This will be the last one we do for this lesson, and we'll finish the rest tomorrow. Move that out of the way. All right, so first things first, we want to factor, and then we're going to find the zeros of the denominator. So if I factor this, this is a difference of 2 squares. So we have 2 times x plus 3 times x minus 3 over x plus 2 times x minus 2. So the zeros of the denominator are x equals plus or minus 2. So we need to figure out, are those vertical asymptotes or are they holes in my graph? Notice there are no common factors between the numerator and denominator, so these could not possibly be a hole. So I already know there's none. So these are going to be vertical asymptotes at x equals 2 and x equals -2. So the domain is all real numbers but -2 and 2. And then if we want to find our x-intercept, again, it's the zeros in the numerator as long as they're not zeros in the denominator, because again, when you multiply, if you set this equal to 0 and you multiply this by 0, it goes away. So I'm not going to write the whole thing this time. I'm just going to write the 0 equals 2 times x plus 3 times x minus 3. So really you're dividing this 2 out. So 0 divided by 2 is 2, so you don't really have to worry about that 2 in front. It doesn't have a variable attached to it, so it doesn't do anything. So we have 0 equals x plus 3, 0 equals x minus 3, so we get x equals -3 and x equals 3. So our x-intercepts are -3, 0 and +3, 0. The y-intercept, we are going to plug 0 in for x and solve. So you can do either the factored form or the original one, doesn't matter. So if I plug this in to my original one, I would have 2 times 0 squared, which is 0 minus 9, over 0 squared minus 4. So that gives us negative 18 over negative 4, which is 9 halves. So 0, 9 halves, or 4.5. So then the horizontal asymptote, the degree of the numerator, if you were to multiply this by distributing in, you would get 2x squared minus 9 for standard form. So the degree of the numerator is 2 over degree 2. This means that the numerator degree equals the denominator degree. So we're going to look at the ratio of leading coefficients. This is 2 over 1. So y equals 2 for the horizontal asymptote. So on my graph, I have a vertical asymptote, 2 of them. So we have vertical asymptote at negative 2 and positive 2. And then at y equals positive 2 for the horizontal asymptote. So then for this, I'm going to graph my intercepts negative 1, 2, something 1, 2, 3 would be here, positive 3. And then my y-intercept is at 0, 9 halves, or 4.5, which would be in between right here. So this is nice because I'm looking for in each region where my vertical asymptotes, I need something to the left and to the right. So on the very left side, I know this is going to follow along my horizontal asymptote, and this one's going to follow my vertical asymptote going down. And then same thing on this side. And in the middle, I know my graph is going to be making a parabolic shape going up and not down, because if the graph were going down like this and this, notice you would have to have 2 more x-intercepts, and we do not. So you know your graph has to go up. So our graph would look like that. And then our end behavior would be the limit as x approaches plus or minus infinity, and the function is s of x, or s of x is equal to 2, because that's where our horizontal asymptote is at. And that is all we're going to do for today. We'll finish up 4, 5, and 6 tomorrow.